The trust, has been driving researchers in many fields. So it brought the new mechanical motors, mechanical structures, technologies, so that the robots were able to perform more complicated tasks in service robotics, in healthcare, in medical application, and again in manufacturing, performing co-manipulation tasks. All of those tasks and applications require physical interaction. Of course, robots can also interact with the environment through their vision, through their acoustic sensors. However, any task considered in this world requires physical interaction. About the physical interaction, robots always get the data through their tactile feedback. Then, using this tactile feedback, robots control and perform different tasks. Tactile feedback has been shown to be very important even in human hand manipulation. There were interesting experiments conducted by Johansson where the same person under two different conditions were asked to manipulate objects to fire a match. So at the first condition, the person didn't have tactile feedback. The fingertips were anesthetized. This we can repeat at homes by touching ice for some time and temporarily have our tactile feedback anesthetized for a while. Under that condition, we see that it's hard to manipulate. However, in the presence of the sense of touch, we can manipulate objects even without the vision, fast and dexterously. For robots, it's the same. If the robots cannot sense the contact, the success of the task is not guaranteed. This is because if the robots relies only on the image sensors, the image is very heavy data stream. Then there can be camera occlusions when the robot is manipulating an object. The occlusions can appear due to the robot's hand itself. Then, if the robot cannot sense the local contact, this will reduce the robustness of a manipulation. So, the challenge that is put in our research is to make robots be able to explore unknown environment, to recognize objects, to manipulate objects, and to assist people in heavy load sharings by co-manipulation. Thus, as in humans, the robot should sense the contact frame, and get some data from the contact. Then the robot should compute the motor commands according to the tactile feedback that it has in order to perform different applications. So we propose the following tactile servoing framework where the robot is interacting with the environment. Then, through its perception system, it gets the contact signals and analyzes that contact signals. This tactile data is then feed-forwarded and feed back to the tactile controller. Given some task, desired task, the controller controls the state of the robot that is interacting with the environment. So given a different control scenarios, different applications, there are different tasks. The different tasks they have different desired contact frames. Therefore, tactile controller should make the errors between the feedback and the desired frames convert to 0 in order to perform those tasks. So that's why we propose some unified framework. And each section, we will show our all contributions to the corresponding computational blocks. So the research that has been conducted in Thesis was implemented in 2 robotic experimental setups. One with the KUKA torque control robot arm, 7 degrees of freedom. The second with the shadow robot arm, pneumatic, actuated by air pressure compressor, with the tactile sensing array attached on the end effector, and the torque sensors that were attached to the end effectors were served as an observers. So the first contribution is in tactile features. we developed the tactile sense features. Those the features are analyzed by the tactile sensors. There can be different types of sensors. First of all, the conventional sensors, force torque sensors, that can sense the force at the contact point. However, those sensors provide only single point contact measurements, one vector per contact. There are other types of sensors that can sense pressure variations at the contact level. So when the finger, for instance, is sliding over the surface, we can sense the pressure variations or vibrations. However, those sensors cannot sense the either force or detect the contact point location. And then finally, there are pressure sensing arrays that can provide the spatial information about the contact. So when there is an interaction between an object and when the sensor, those sensors can provide the spatial information about the contact. Those sensors are constructed with from small force sensing cells, so-called tactiles. Those sensors measure normal force only. They are arranged in row column-wise structure. So when there is an object is in contact with such a sensor, there is a contact frame. We consider in our research two types of contact. For the point contact, when, for example, a spherical object is in contact with a sensing surface, there is a point contact, and the edge contact type. So when, for instance, the sensing surface is in contact with the edge of the table, there is the edge contact type. So we set here a question, what are the measures of the contact frame that can be controlled? So the work has been conducted so far. It began in 1979, when the first, one of the first sensors were created having a cylindrical shape with 133 sensors. The sensor was created in Toulouse. However, such kind of approach with a cylindrical shape of the sensors could sense only coordinates of the contact at a single contact again, and it required additional exploratory movements in order to detect the contact frame. Then later on, when it became possible to construct the sensors in a row column wise, so the spatial resolution of such sensors became higher, researchers have taken another approach of considering the deformations of the sensing surface by analyzing the strain and stress analysis, applying some elasticity theory. However, those approaches are relatively slower. They were slower and they were not couldn't be used in the real-time applications. Then later on, another approach appeared when the contact frame, the pressure distribution, has been analyzed by considering it as a grayscale image. So the pressure at each tactile was mapped to intensity value inside the tactile corresponding coordinate in the tactile image. So the pressure distribution was mapped to grayscale image. By mapping each pressure value of a tactile to a grayscale value, the intensity of a tactile in pixel in the image. So those approaches could be used in the real-time applications. This has been performed in the following way. The image space that had the tactile image sensor is reduced to a feature space by computing image moments, applying image processing techniques. So the contact frame between an object and such a tactile sensing array now is represented by a feature vector. So for different type of a contact, there is a different feature vector. When, for example, there is a point contact type, so when the surface is in contact with a spherical object, we can extract the center of pressure along x-axis, a center of pressure along vertical axis, and the force, which is proportional to the deformations of the surface. Thus, a three-dimensional vector can be created. For the edge contact point contact type, in addition to those three features, we can extract also the angle of the edge. So the orientation of the edge around z-axis can be extracted. And thus we create a four-dimensional feature vector about the contact frame. However, this is not enough in order to represent all of the deformations. So here is our contribution. When there is a non-uniform line force applied to the sensing surface, we can detect these deformations through using one more feature. So previously it was assumed that the edge that is in contact with the sensors is always under uniform force line distribution. Thus there were only four-dimensional feature vector. In order to find the features for this type of deformations, we propose the following rather simple algorithm. So when there is a deformation in the sensing surface, we can compute the center of pressure, then threshold the image that is in contact, and calculate the center of contact. Then the difference between the center of pressure and center of contact will represent this the rotational deformations, or the moment of force applied to the sensing surface, assuming that all tactiles they have the same compliance constant. So this is similar to the robot locomotion. When the robot is staying and not applying any moment of force in the equilibrium point, there is the term called zero moment point. In similar way, we define this feature as a zero moment point feature that represents the moment of force applied to the sensing surface. And this is proportional to the difference between center of pressure and center of contact. On each axis, there are different, this feature works for two different directions. So, thus we created the contact frame that is fully defined. For the edge contact point type, there is a center of pressure and the force. So the contact frame is now is controlled by a robot. For the edge contact type, the advantage is here that in addition to the moment of force applied to an object, we can also control the moment of force during the partial contact. So when the edge is not infinite in the sensing surface, a robot still can estimate the moment of force and apply the pressure distribution to an object so that it's evenly aligned. How to control such a robot, I will discuss next. So in a tactile controller, we will develop such a control algorithm that takes those contact frames and control and moves the end effector of a robot. So the problem is following: when there is an object or environment which is in contact with the sensing surface of the sensor, that is attached to the end effector of a serial link robot manipulator, simply robot arm. There are several contact frames. The base frame of a robot, the end effector frame, the sensor frame, and the contact frame. The goal is here is to control and compute all the joint angles of a robot so that we control the contact frame in a desired manner. We assume that the environment is changing not so fast, so we assume the quasi-static case. Then we assume that here the contact appears only on the end effector, not on the other links. And we also assume that for sliding motions, for instance, there are no friction forces. However, for manipulation tasks, we assume that there is a friction, enough friction. So previously, this work has been performed in the following way. The researchers since 1991 applied tactile serving algorithms in order to perform exploratory tasks by sliding over an edge. So in Berger et al. In 1991, they developed a tactile controller by taking a robot controller that works in the Cartesian space, the robot is moving in the Cartesian space its end effector. Then the end effector is the pose of the end effector at each time control step is modified according to the feedback and desired tactile features. Then in 1994, this was extended to control the edge contact type and the point contact type. And the most recent approach is able to, through the projection matrix, to control the edge contact point type and the point contact type and increase the contact area by rotating around the contact frame. This I will explain in the following. So far it was proposed that there are 4 features for the edge contact type that are mapped to the 6-dimensional Cartesian space. So it's x, y, z, and the rotations around each axis. Yeah. And in most recent approach, the inverse tactile Jacobian has been proposed in order to map those 4 features in the 6-dimensional Cartesian space of a robot arm, the end effector of a robot arm. So we propose that actually it's possible by those EMP features introduced before to control the 6 features in the 6-dimensional Cartesian space directly. And also that during the manipulation there are cases when the point contact appears and switches to the edge contact type. So we can develop such a inverse tactile Jacobian that can reactively adapt to these new conditions and switch its matrix according to the type of contact. So we took the approach that exists in the robotics literature, the hybrid external position force control, where a robot is operating in the Cartesian space and the actual pose each time is modified according to the force that is given by force sensors. So at each time step, the desired pose of the end effector is modified according to the interaction force. Here we replace the force vector by tactile features. And thus we develop the external tactile position controller. This controller looks in the following way. It has a tactile feature error vector where we compute the features from the contact frame. Then this tactile feature error, feedback error, is mapped to another feature vector through our touch-dependent inverse tactile Jacobian. Then those vectors, depending on the contact type, are feeded back to in order to compute the tactile feature error. Then we introduced the projection matrix that maps those feature errors to the Cartesian space contact frame represented in the Cartesian space in a desired way. Then finally, those errors are fitted to PI regulators and transformed from the sensing frame to the base frame of a robot. Then those commands of the desired pose are sent to desired pose of an end effector or a robot controller. The robot can be controlled in the joint position control mode or the torque control mode. Here we assume that the end effector pose we can control that the pose always is in dexterous space of a robot manipulator. So we don't reach to the singular position points or we are not in those positions where we cannot reach those end effector poses. So the feature vector depends on the contact type. So for the firstly, we computed the center of pressure, force, and center of contact, and the orientation of an edge. Yeah. Then, depending on the contact type, those feature vectors can be different, have different dimension. So for the point contact type, the center of pressure and center of contact are equal, whereas for the edge it can be different, as was shown, because the edge can apply some moment of force. In order to distinguish between those two contact types, we apply the principal component analysis. So when there is an agent value corresponding to one of the orthogonal agent vectors is k times higher than another agent vector, we detect that such a contact type as an edge contact type. However, when those agent values are relatively similar, such a contact is considered to be point contact type. Okay? This is working as follows. So, for instance, when there is a robot interacting with the environment and exploring it, and there is some bar which was not previously aligned and was not parallel, at the first time the type of contact can have the point contact type. Yep. However, with the time when the robot adapts to this bar, applies the force evenly, the contact type can switch to the edge contact type. This is taken to the controller's feedback by inverse tactile Jacobian. It looks like the number of elements in the tactile Jacobian depends on the number of degrees of freedom of a robot. However, here we assume that there is we can directly map to the end effector pose. So the 6-dimensional Cartesian space and 6 features. That's why the inverse tactile Jacobian has a 6x6 dimension. There are 2 elements inside the tactile Jacobian that that are dependent on the type of a contact. So the initial feature vector is mapped to another feature vector through this tactile Jacobian matrix. Then, given a desired feature vector, we compute finally an error vector that should be taken by controller in order to converge it to 0. So during those contacts, the vector works as follows. When there is a point contact switches to the edge contact type, the inverse tactile Jacobian changes its form. So the next part of the controller is the projection matrix. So in order to map those errors in different ways, we can actually control either orientation of the edge or the force or the center of contact. In order to be able to change between those tasks, we can introduce the projection matrix. So here you see the control of the orientation of the edge, and here you see the control of the center of contact. This is realized due to the projection matrix. Okay? However, we also can use such a projection matrix in order to perform different tasks, as for example sliding over the edge. So when the projection matrix is set, the first element of the projection matrix is equal to 1, the end effector moves along the bar by controlling the center of contact along its horizontal axis. And when the element is 0, controller does not move. Finally, the output of the projection matrix is fed to PI regulators and then transformed to the base frame of a robot. This is important because the different robots have different joint properties and different structures. So the links of a robot can be different, number of joints can be different. That's why the frame transformation is applied. And since the environment can have different stiffness, can be flexible, deformable or rigid, the different gains for PI regulators are needed. So that's where we developed a control algorithm that takes as an input the desired features, feedback features, this actual pose. Then the inverse tactile Jacobian is updated due to the contact type. Then a feature error is computed. This feature error is mapped through a projection matrix in order to perform different tasks. Then this output of the projection matrix is fed to the PI regulators in order to make the error converge to 0. Then those errors that are represented in the sensing frame are mapped to the base frame. The error converges, the robustness of the system, is guaranteed by PI regulators, as it can be since it's second order system, we can tune those gains in the PI regulator so that it will be damped or critically damped. And we assume that we avoid the singular positions. For instance, when there is an edge in the contact, it can be case when the orientation of the edge is 180 degrees, which means that it can be 0 or 180. That's why we limit the orientation of the edge in the contact. Moreover, we assume that the affordances for a robot are known in advance, which means that the task, the action that can be performed over an object is known in advance. So in the directions where force can be controlled, we cannot control velocity, and vice versa. So when there is an object which is rigidly attached to an environment, we can control force applied to an object, but we cannot move that object. And vice versa, if the object is lying on the surface and without, we assume that there is no friction force, we cannot control the force because we cannot measure the force, but we can control the velocity, how we manipulate the objects. That's why the natural and artificial constraints for different contact types and tasks should be considered. So for the point contact type, we can control the following forces and velocities, and for the edge contact type, we can control other complementary force and velocity vectors. Okay. So the advantage of this controller is that the ability to align with some metal bar that was initially not aligned with the sensing surface, even in the case when this bar was in the partial contact. So in the most recent approach, such kind of task fails since the end effector keeps rotating around that edge. And with the proposed inverse tactile Jacobian matrix and the edge detection algorithm, we can align with the edge that was partial contact with the sensing surface. Before this, always the edge was assumed to be infinite in the sensing surface. Using the MP feature, it's possible to apply the moment of force on this edge so that the flying force will be evenly aligned. That's why we developed the tactile controller, and this tactile controller should serve in order to perform different tasks. Given different control scenarios, there are different desired features, and for the following tasks, we developed the different tactile desired features. So we performed the deformable object recognition, exploration of environment, then a manipulation of different objects. We can even reconstruct the shape of a known object and perform co-manipulation tasks. In the following, each task will be considered and shown. So, and each task has its own feature vector, the projection matrix, and the inverse tactile Jacobian that always depend on the contact. So the task description layer sets those commands to the tactile controller in order to perform different tasks. In the exploratory motions, we can set the tactile controller in order to slide over the bar. So when there is a bar in the environment which is the orientation and position of which was not known in advance and there is no vision, we can explore such a bar by setting the tactile controller in order to control the center of contact in horizontal axis, center of contact in vertical axis in order to keep the contact in the middle. We can control the force and then apply the moment of force and control the orientation of the edge so that the bar will be always parallel to the sensing surface. Moreover, with the proposed MP feature control, by controlling all of the 6 features in the 6-dimensional space, we are able to control the end effector so that it follows the bar that is bended not only in the planar surface but also in the surface which is perpendicular to the sensing frame. So by the controlling the ZMP feature at the 0, we can adapt at each time when there is new radius of curvature of the bar. We compare this with the baseline approach, and you see here that without controlling the ZMP feature, the end effector applies too high moment of force. By using the control of the orientation of the edge, we can also control the exploratory movements when the bar is bended in the three-dimensional, in the planar and in the perpendicular planar planes. So this also enables to explore environment with a variant stiffness. This has not been conducted before using such a tactile sensing arrays. So this experiment was shown first time here at ISIR. So when there is a metal bar that is attached from one side of the end and the other side is floating, the end effector, when end effector slides over this bar, the bar bends, and since the bar has different stiffness values at each coordinate along the bar, the radius of curvature can be different. These new radius of curvatures are taken in by the controller by controlling the ZMP feature. So at the end, we can actually also reconstruct one of the property of such a bar and use it to recognize such a metal bar by plotting the stiffness function over the length of the bar. So as further we are from the rigid point, the stiffness is lower. However, due to some sensor noise, the rotational action of the end effector in alignment with the bar has some oscillations. This is only due to the sensor noise, and also we assume that there are no friction forces during the sliding motions. However, there are always friction forces. Even we added some plastic tape on the sensing surface in order to have less the friction forces. So this plot shows the evolution of the end effector pose around the y-axis during the exploratory movements. Another task to be considered is the recognition of the objects. So we can apply force in order to squeeze objects by looking at the propagation of the contact area and forces. We can compare two different objects. So given two objects that are deformable and rigid, we can differentiate based on the history of the responses to different objects. We can apply dynamic time warping algorithm in order to compute the distances between those objects. So it has been shown that the distance between the rigid ball and the soft ball in a contact area is smaller when the distance between a soft foam and soft ball is smaller in force responses. Another task that was conducted using this tactile controller is manipulation of objects by rolling them. So given a known radius of an object, we can control the angle of rotation of an object based on the center of contacts, and given some formula of arc lengths. So the arc lengths and the angle of rotation are naturally constrained. Therefore, we can rotate an object by a given angle. So during the manipulation, we can control the moment of force that is applied even in the case even when there are obstacles on the surface. So during such manipulation, the end effector using the ZMP feature aligns with those obstacles, and we compare the results with ZMP feature and without the ZMP feature. So here I want to show what happens when we use such an At the moment when the end effector rolls over an obstacle, it adapts during that manipulation action. Then in order to find the performance of these manipulation options, we perform the task of by rolling the object in the, by following the time square function with the different periods. And the bandwidth was found to be equal to 0.1 Hertz. However, the PID gains can be tuned in order to perform such a task faster. Then, if the shape of an object is not known in advance, we can reconstruct the shape of an object after the manipulation. So when, for example, there is ellipsoid shaped object, during the manipulation of such an object, the pole and the vector pose along z-axis changes, so we can find the minimum and maximum coordinates. Given the changes in the center of contact and the position along z-axis, we can reconstruct the ellipsoid shape with its major and minor axes. So finally, we implemented such a controller in order to perform co-manipulation tasks. So for example, when there is a tray in between a human operator or environment with a rotational bearing, the plate can rotate freely so that it can flips over. In order to keep this tray in the equilibrium point, the end effector can adapt to this new condition and control the center of mass at the equilibrium point. So by controlling the end effector contact frame with the ZMP feature at the desired value, the end effector can keep the tray at equilibrium point even when there are changes in the center of mass of the tray. So for each new different state, the end effector is trying to balance this tray so that the tray is not flipping over. At that time, we are controlling the all of the 6 features. Then this was the final task that was performed during the research. With this, I would like to conclude that we contributed in the to touch-driven control motions by proposing the unified approach, developed tactile feature extractor, tactile controller, with the inverse tactile Jacobian that takes into account the edge or point contact type, and developed a projection matrix that enables to perform co-manipulation tasks. This work has been published in the following publications. So the future work that should be considered is to apply such a control to multi-point contact control. So for example, as a robot hand has different, many links, many fingers, the number of contacts during the interaction is not only one, there are many of them. So in order to perform manipulation tasks, the robot arm can perform exploratory movements in natural way. As the humans, when we don't know in advance the shape of an object and the revision is not known, we perform in-hand manipulation or finger gating or regrasping it. So by increasing the number of contact points, we can reconstruct the shape finally. This, the same approach has been applied in the autonomous local localization mapping approaches, when the robot moves around the same surface many times in order to simultaneously build and find its position inside the area. In the same way, we can manipulate objects with unknown shapes in order to reconstruct that shape, to detect, distinguish between different shapes. The interesting point here is to find the policy to do the second grasp or finger gating in order to have the most differentiable information about 2 different objects or 2 different hypotheses about the contact shape, the object shape. The preliminary work has been conducted, so together with CEA List Lab, in the CEA they developed a capacitive tactile skin that should be attached to a robot hand in order to perform such a tasks, where the a robot hand is considered as, for example, in handover tasks here. So when the object firstly aligns with the most comfortable grasp, then based on the tactile feedback, this object can be grasped. Well, with this I would like to thank all of those people here from the jury and from the lab with whom I've been working together, with whom I got some help, and with whom I published some papers. And I would like to thank all of the team at ESIR and the financial support from Nazarbayev University. Thank you very much.
Thank you very much. Now your talk is open to discussion, and I will first give the talk to your supervisor. And first, Professor Pierre.
Thank you very much, President. First, I would like to thank Veronique for inviting me. It's always a pleasure for me to come and visit your lab in Paris. So I would like to maybe in English or
Je vais essayer en français, mais après, sinon, je vais parler en anglais.
maybe better in English. So first, I would like to congratulate you for your document. It was really a big pleasure for me to read your document. It's very important work, and also it's very important to simulate, of course, but also to improve your proposals. And you really did many experiments in order to improve all your investigations. So I would like to congratulate you for this very important, impressive work concerning the experimental demonstration that you did. So your presentation was very nice with many impressive experimentations. So of course, as it's an interesting work, I have many questions. So I'm going to try to ask, not to take too much time maybe, because there are many persons with me. So first, as you are now an expert in the field of tactile sensors, and also you have a real and big experience in tactile sensing, I would like first to ask you, with your feedback and with your expertise, the state-of-art you lead, what is for you today the best technology for tactile sensing in the field of grasping and also inside-hand manipulation?
Okay, so I can answer in this following two ways, okay? If we are looking for the expensive solution or a cheap solution. So for the expensive solution, it would be biotactile sensors from the United States that are integrated with the current version of the shadow hand. Because they actually, as a finger, our human fingers, they have some fluid inside, yeah? Those biotac sensors, they also have fluid inside. So actually, the studies of the human touch and putting some algorithms from the human hands in autonomous robots can be more, I would say, natural.
But with these sensors, do you also have compliant material on the surface of the sensor or not?
No,
in the commercial
it's only on the fingertips.
Okay.
So it's not, this sensor cannot be used on the skin.
Yes.
For the skin, the best solution is, it's actually I've seen the sensors from the Japan, where they use the stitch technology. So it was some titanium or golden wires sticked in the mesh way to each other. So by pushing higher at some coordinate, the resistance changes. Thus we can detect the
And
the contact.
it's also matrix?
It's also matrix, yeah, but it's a fabric one.
Oh, okay, so it's flexible.
It's flexible, yeah.
Yes.
And there is another solution in Germany, in Bielefeld, where they use the resistive technology by creating the fabric glove, tactile skin. So actually, by having a tactile glove that can be put on the hand of human hand, it also can be put on the robot hand directly. And it's fabric based, but it's not so stable as far as I know.
So did you try other sensors? Because, of course, my second question will be, why did you choose the sensor from Weiss?
Yeah, so
Because,
before we tried with a pressure profile sensor from the United States, they had a much lower resolution, and the sensitivity was lower. So in order to perform different tasks, we had to push harder. And we could also use the force-torque sensors that are attached on the fingertips of a robot hand that we have now currently, but such sensor can detect only a single contact point. So if we press from two sides, the data output gets really noisy.
And for the Weiss sensor, the compliant material is already on the commercial proposal, or did you choose the compliant material on the surface of the sensor?
No, it's always with the piezoresistive rubber, the conductive rubber.
Okay,
So we didn't choose, we only did some calibrations of sensing surface.
And you did